Hello everyone. In this lecture, we are going to study the classical physics. In the part 2, we are going to study the current and the magnetic field. First chapter is the current and magnetic field. Second chapter is Ampere's law. Third chapter is Faraday's law. Fourth chapter is Maxwell's equations. And the final chapter is electromagnetic waves. So today we are going to study the first chapters, current and magnetic field. First section is a current. Second section is a magnetic and magnetic field. Third section is a Lorentz force. First topic is a current. Current is a motion of charges from one region to another region. Actually, the electron is moving random directions. Sometimes happen to collide with the ions. The speed of the electron is estimated 10 to 6 meters per second. So to understand the magnitude of the speed of the electrons, we have to use quantum physics, Fermi energy of the electrons. So if you have studied quantum physics, you might know the Fermi energies. If you have never studied the Fermi energies, you could take lecture for the modern physics, and I'm going to explain the Fermi energies. Fermi energy is written by the h bar squares over 2m sub e times 3 pi squares n is the number of the particles over v is the volumes 2 over 3. For the h bar is a Planck constant. It's going to be 1.05 times 10 to minus 34 joule second. Number density of electrons in metals. We are going to get these numbers in the practice. It's about 9 times 10 to 28 electrons per cubic meters. And the electron mass 9.11 times 10 to minus 31 kilogram. If you substitute these numbers, you will get 1.2 times 10 to minus 18 joule. This is a Fermi energy. So from the Fermi energy, we can estimate the speed of an electrons in metals. So energy is equal to the kinetic energy, 1 over 2 m sub e v squares. So from these equations, we have an expression for the speed. It expressed as square root 2 e sub f Fermi energy over m sub e. You can substitute these numbers. It's about 2 times 10 to 6 meters per second. If you consider the electron has the energy of the Fermi energy, then we can estimate the speed of the electrons is about 10 to 6 meters per second. About 1000 kilometers per second. This is the random motions of the electrons. In the conductors, electric field is applied. Then electron is moving in one direction. So in this case, electric field is directed toward the left. Then electron is moving to the right. Then drift velocity becomes like a 10 to minus 4 meters per second. You might be so surprised. This is really slow velocities. Drift velocity is really slow compared with the random speed of an electron, 10 to 6 meters per second. Because of this drift velocities, electron is moving to the right, and this produces a current. So direction of the current. If we consider semiconductors, positive charge is responsible for the current. In the metals, electron is responsible for the current. So direction of the motion of the positive charge is the same with the direction of the electric field, but in the metals, electrons has the opposite directions with respect to the direction of the electric field. So in the semiconductors, we have two types of the semiconductors. negative semiconductors or positive semiconductors. In the negative semiconductors, actually we consider silicon as a base, and the silicon has a 4 outer electrons. So 4 outer electrons. So like this, electron is shared with a neighbor's silicons. So this is the situation. And we put a phosphorus. So phosphorus has one more electrons, extra electron. So we call the negative semiconductors. The electron is responsible for the current. The positive semiconductors as a base we consider silicon. So instead of the silicons or phosphorus, we introduce the boron. So boron has only the 3 outer electrons. So we are missing part. We call that this is hole because the electron cannot be occupied by the boron and the silicons. So this hole has a positive charge. So this hole is moving in the same direction with the electric field. So this is responsible for the current in the case of the semiconductors. Then for the current, we'd like to find out the expression to describe the current. Current is a net charge flowing through the areas per unit times. So this is the cross sections of the wires. Then the wire has an area of the A. Then if we consider cylinders, height of the cylinder is V sub d times dt. This is the height. Height times the area gives us the volumes. So this corresponds to the volume. If you multiply the volume and the number densities, n is the number density of the charge. So this becomes a total number of the charges passing through these areas after the time of the dt. Because all the electrons can pass through these areas after the time of the dt, even if the electron is really close to these bottoms of the cylinders. It can reach the other side of the cylinders and they pass through these areas. And if you multiply the charge, you can find the total amount of charge passing through these areas, dq, d capital Q. And the current is expressed dq dt. This is the definition of the current. I is given by n times number density times area times the drift velocity, the v sub d. And the unit of the current is expressed amperes. Ampere is expressed as coulomb per second. And I would like to introduce the new term of the current densities. So current per unit areas, if you divide it by the area of the wires, it becomes the current per unit area is equal to the current densities. So I is divided by the area of the wires, it becomes current densities Q times N times drift velocities. And the unit of the current density is ampere over square meters because the area of A has a unit of the square meters. And the vector current densities, we can define vector I is expressed using the drift velocity of the v sub d. The drift velocities, how can you find out the drift velocities? Before the collision with the ions, electron freely moving, accelerating by the electric field. Acceleration of the electrons can be obtained by the equation of motion. M is the mass of the electrons, acceleration equal F. F is a force acting on the electrons is equal to Q is a charge times the electric field. So from this equation we can find that acceleration is given by the Q over M times the electric field. By assuming the electron stops after the collisions, we have average velocities. So V is given by A times T. And as a T, we could consider the mean collision times of the electrons and the ions. A times tau. This is tau is the average time between the collision. Then V can be expressed this expression, and then you substitute this QE over M's. Then it becomes V is expressed. This is the drift velocity. Then current density is expressed Q times M times drift velocities. Then substitute this expression here. Then current density is N times Q square tau over M times electric field. This is the current density. Current density is parallel to the electric field. We have two types of the currents, direct and alternating current. In the case of the direct current, direction of the current doesn't change. In the alternating current, direction of the current is changing with times. Okay, so I explained the current in these sections. This is the end of this session.